Yeah, so thank you, first of all, everyone, for coming, and obviously Alex for giving the first virtual teaching spotlight of the semester. So Alex Kontorovich is going to tell us about teaching real analysis as a video game. And just as an aside, if anyone is interested in giving any other talks about education and like either AI or anything else that you would find useful, please reach out to either me or Sheila, who is also like co-organizing like these events. But yeah, I'll just be quiet and let Alex speak. Thanks again.
Okay, so thank you so much for the opportunity to speak here. It's great to have an opportunity to download some of the thoughts that I've been having over the semester as I try to teach real analysis as a video game. So this is 311, a branch of, I guess this is 311H, the honors section, where they were unwitting, uh, guinea pigs in my little experiment here. So let me tell you how it's going. So. Um, the impetus for this, I mean, there's a wide variety of things, but I just imagine the world where this is how you teach chess to people. You say, okay, so here was the game. I want to tell you this really amazing game. So knight went to f3, the other knight went to f6. Then white went c4, black responded g6, knight c8, and so on. Okay? And then at move 11, can you imagine knight f4? How did they do that? That's crazy. What are they talking about? To most of us, to the vast majority, I don't know, maybe there's some chess aficionados here who know exactly what's going on here. To me, at least, this is complete abject nonsense. I can't understand what's going on because I don't have that game board in my mind's eye. I haven't played enough chess that I can just instantaneously process everything that's happening. But this, gets easier with practice. But until then, just show me the game board. Show me what the actual game looks like. There's knight going to f3. There's the other knight responding with f6. There's the pawn going to c4 and g6 or whatever. Okay, so you get to actually see the game happening. That's how we learn chess. Okay, now how do we teach math? So I claim that this is exactly how we teach math. If you think about our the proof that every single one of you knows, the square root of 2 is irrational. Okay, if not, then it's equal to a fraction of lowest terms. So square both sides, cross multiply, and you get the p squared is equal to 2q squared. So p has to be even, yada yada. You can finish the proof in a few lines from there. Right? Makes complete sense to everybody. To newcomers to the game of mathematics, this is as impenetrable as knight f2, knight whatever, g6. It's just, they're instructions, but the instructions don't show you the game. Show me the game board, and I'll have a much easier time of understanding what's happening from one instruction to the next. So let's look at the actual game boards. So what are the actual game boards? Well, there's the rational numbers, and there's the casting of the rational numbers to the real numbers. So rational numbers are like, 3 over 1 is a rational number, but a real number is equivalence classes of Cauchy sequences of rationals. So 3 over 1 actually has to get sent to 3 over 1, comma, 3 over 1, comma, 3 over 1, an infinite constant sequence of 3 over 1, together with the proof that that infinite sequence is Cauchy. So that's what this casting function is, and the range of that function is the rational numbers embedded inside the real numbers, and the claim is that square root of 2 is not one of those. Okay, so forget it. Maybe that's too much information. Maybe you don't actually want to know that, but let's keep going with this. So if not, what does it mean if not? If not means let's add the hypothesis that square root of 2 is in the range, and our new goal is to prove a contradiction. So the game has changed. The knight actually moved. And now we're in a new situation where what we're trying to prove is not that square root of 2 is irrational. What we're trying to prove is a contradiction. Okay, so if it's not the case, if we're in this situation where we have this hypothesis the square root of 2 is rational, then it's equal to a fraction of the lowest terms. So in other words, we have a new situation. The new game board is there exist integers p and q where q is not 0 and the GCD of p and q is 1. They're coprime. And p over q, now the up arrows is that p turns into a real number and q turns into a real number. Again, they're integers, so they have to be cast to rationals and then real numbers. And then this ratio of real numbers is equal to the square root of 2 as a real number. Okay, and then we can square both sides. Fine, we can square both sides and we can cross multiply. So we're just doing a bunch of algebra and still we're trying to prove false. Okay, so now you get to see the game board at every single level of interaction. And so my claim, now if you're writing on the chalkboard, it's just infeasible to write every single game board. Just like if you're teaching chess, you would not draw an 8 by 8 grid and shade in, every other square and draw where the knights are and then erase where the knight was and move the knight and put him somewhere else. I mean, it would be crazy to try to do that. They have, when you're teaching chess, you have a way of demonstrating the game board at every location. But until now, we didn't have a way of doing that with mathematics. And now we do. So we would never do this when teaching. First of all, it would be too long and cumbersome. Second of all, well, we all learned this without those game boards somehow. Of course, many of our classmates didn't really learn it properly and stopped doing mathematics. Um, in fact, there's another point, which is that the chess players who become professionals because they're able to think 7 moves ahead. So they can move those chessboards in their head exactly in the same way as all of you can develop the arguments just by following the instructions without seeing and developing the game boards in your mind. So I think that it's actually to do math at a high level, you do need to have those chessboards. Um, just like looking ahead in chess. But when you're starting out, let's ease the grade just a little bit by giving people the chessboards. And so that's basically what this experiment was about. When you're teaching a course with Lean, where you're writing the code live, trying to solve the video game live, the game board's automatically there. And so that's what this experiment has been. So any questions so far? Let me stop there before I go somewhere else. So far, so good. Okay, so here's what the experiment looks like. I'm going to run a local version, but let me put in the chat the global version so that you can all play with it at your leisure. So there's the version that's sitting there online, and then there's the let me close this one so I make sure I stay on my version. Okay, so here's the game. The game comes with a course website. So the course website, let me just click through to the course website so you see what it looks like. The course website has all of the lectures recorded because I'm anyway sharing my screen on a computer to play the video game, so I may as well hit record on Zoom and upload it to YouTube so the students can review the lectures anytime they want. All of the lectures come with lecture notes that are generated from the discussion that I have by LLM. And so it looks like this together with the actual lecture. The actual lecture is handwritten. So you'll see the chicken scratch at the end, which is, we're talking as if we're talking on the blackboard. And then that gets converted into actual mathematics together with the lean proofs of the statements. So that's kind of the human side of things. Let's go back to the video game. So the video game has lots of levels. Basically, every lecture, right? This isn't how it's going to be in the future, but right now, the way it's designed, every lecture comes with a problem set. So for lecture 1, there's problem set 1, then there's lecture 2, and problem set 2, and lecture 3, and so on. And there's a dependency graph of, I'm going to give lecture 3 before lecture 2 is due. And so lecture 2 or whatever, before the problem set is due. So lecture 3 doesn't depend on this problem set, but then the later lecture is due, and so on. Let's just play a little bit of the game so you get a sense of what it's like to do this. So far, so good. So here's the beginning. So at the beginning of every level is an opportunity to have a discussion without lean at all. And so here, the way I try to introduce any difficult topics before we do any coding is a discussion between Simplicio and Socrates. Okay, can you see this? Should I make it a little larger? A little larger? No, it's okay. Well, I'll make it just a little larger. Okay. So this is lecture 1. So the first question is, what the hell are we doing here? Why are you taking real analysis? What is real analysis? Well, it's calculus. Didn't I just take like 4 semesters of calculus? Why am I doing it again? Okay, so, what was calculus? Oh, right, there's this thing called slope of a tangent line. That's a derivative. There's this thing called, Riemann integral, and that's a limit. They're both limits. You know the fundamental theorems. There's all this great mathematics that happened. And then in the 19th century, a guy named Cauchy comes along and says, you can take limits of continuous functions are continuous. And another guy named Fourier who comes along and says, actually, I can take sines and cosines, and in the limit, I'll get this, discontinuous sawtooth function. So we broke math, and now we have to fix it. And the entire 19th century was devoted to fixing math, to the extent that people couldn't figure out what the real numbers were. There were arguments about the real numbers. It's like Simplicia says, "What do you mean? I know what they are. Here they are. Here's the numbers on the real number line. What's the problem?" And then the discussion is, okay, let's prove the intermediate value theorem. The function x squared minus 2 is a nice parabola, and in the rational, it takes rational numbers to rational numbers, and in the rationals, there's a place where it's less than 0, and there's a place where it's greater than 0, and it never actually hits 0. So why is the intermediate value theorem actually true? What about the real numbers as opposed to the rational numbers makes the intermediate value theorem true? Okay, so that's what that little discussion was. And then we jump to level 1. And level 1 starts introducing the way that the game works. So the way the game works is you have a list of theorems. Right now we do not have access to any of the theorems yet. We only have access to one of the tactics, and we don't have access to any of the definitions. So presumably we're supposed to use this tactic. Of course, you can read the text here. You can also ask for help. But the main game takes place right here in the middle. And it says you have an object, which is a real number called x. You have an assumption, a hypothesis called h, which assumes that x is equal to 5. And out of that, you're supposed to prove that x is equal to 5. So this is your goal. The goal is the turnstile. I think of this as like an escape room. The turnstile says, I will not let you pass this turnstile until you provide for me a proof that x is equal to 5, and then you've escaped the room and you win. Okay? So how do I show that x is equal to 5 if I know that x is equal to 5? Well, that's what the apply tactic is for. Apply tactics, I can say apply h. H is the statement that x is equal to 5, and there you go. Now, if you didn't know to do that, let me erase this world. No, it didn't work. Let me try it again. Let me delete this. Let me just delete everything, maybe. So I'm back to level 1. If I didn't think to put apply here, or I didn't want to read all of this stuff, there's also a little hint. Show more help, and then you can write, the hint says, hey, how about you write apply H? Okay. So if you didn't know that, you could do that, and now it says, great, level done, next level. So the next level is going to tell you about what you do if you have the following situation. You have two objects, x and y, and you're trying to prove that x squared plus 2y is equal to x squared plus 2y. So it's no longer apply. I don't have a proof of this anywhere. It's something else. It's the reflexivity of the equal sign. So if I have this literally the same thing on both sides of the equal sign, there's a tactic called REFL, and REFL will prove anything of the form A is equal to A. If you have identical things on both sides, REFL will prove that. So all I have to do, and if I didn't know that, I could click here and say, hey, just write, type the 3 letters REFL and hit enter, or press execute, and this level is done. Okay, so of course we're starting off very easy. In just a minute, we'll jump to something a bit more interesting. Here's a level where you know that x is equal to 2. I was messing around with the kids. They said, let's call this assumption. Does it have to be called H? I said, no, you can call it Alice, you can call it Bob. So it ended up getting called Bob. So Bob is the assumption that x is equal to 2. And now what we're trying to prove is that x plus y is equal to 2 plus y. Well, isn't that REFL or exact? No, it's neither, or apply. It's neither of those things. First, I have to rewrite the fact that x is equal to 2. So if I rewrite Bob, and if you want more help, this will help you. Try rewriting by Bob. And here's where things get interesting. The game changed. This is the first time where we don't simply have a single move and it's checkmate, but we have a single move and then we still have to do something. It's not checkmate. The game's not over. So you see the previous goal state, and now you see the new goal state. And what has happened is Bob was the fact that x is equal to 2, so Lean looked for any appearances of x in the goal. It found one, and it replaced that x by 2. And now our new goal is 2 plus y is equal to 2 plus y. How do we solve 2 plus y equals 2 plus y? Is someone brave enough to type it in the chat? Or unmute? REFL, exactly. Yeah, it's the reflexivity property of the equal sign. So again, that's not something they're going to get a hint about. That's something that they need to start developing how to say these things, and REFL does. Okay, great. Let's just do, maybe I'll skip some of these. Okay, this is the ring tactic. It tells them, I assume you know how to do algebra, and Lean will let you do algebra automatically, so you don't have to do anything. Oh, I can't click next. I guess I have to relax the game so that I can skip levels if I want to. Okay, I want to skip that level. Uh, so great. Lean will do the arithmetic for you, but sometimes I do want to know that you can do the arithmetic. So how about this example? Maybe if I zoom in just a little bit, is that a little better? Uh, if I take x plus y to the fourth, if I multiply all that out, that'll be x to the fourth plus 4 x cubed y plus something x squared y squared, but I don't know what that something is. So the claim is that there exists some constant c, some real number c, so that this identity holds. Can someone suggest what identity, what c should be? Either in the chat or by unmuting. Who remembers Pascal's triangle? Yeah, 6, of course. So what are you supposed to do? If your goal is to show that something exists, then you have to provide that. So you have to say use 6. So use is the word for that. Use 6. And now we have a new goal, which is it true that x plus y to the fourth is equal to all of this? And of course, that's just algebra called ring normal form. Okay, now the game is done. Let's do just a couple more levels so you see what's going on, and then we'll jump to something much more interesting. Um, so here's something. If you want to say for all epsilon positive, of course the positivity has nothing to do with it. It's just an excuse to practice something. In analysis all over the place, there are statements saying for epsilon positive. We have no assumptions. What we want to prove is that for all epsilon positive, some identity holds. So can't I just say REFL? Isn't this the equality, isn't this the equal sign? No, I can't say REFL yet. In fact, if I try to say REFL, we'll get some kind of error message. No, I don't have it starts with a for all epsilon. So first, if you ask for more help, it'll say, why don't you try saying introduce the epsilon? If the goal is to show something for all epsilon, then the first thing you should say is let epsilon be given. So intro epsilon, and once epsilon is given, the new goal is if epsilon is positive, then something happens. So if your goal is P implies Q, the way to prove that is say, so give me P, and then I should prove Q for you. So in the same way that you should say, give me the epsilon, you should also say, give me a proof that epsilon is positive. So this is intro H epsilon. And now we see two steps in the game from the first situation to the second situation where we have an epsilon, and if epsilon is positive, then we need to prove this. Now we have the epsilon. We also know that epsilon is positive, and we need to prove this. And now how do you do it? Yeah, exactly. REFL. Okay, so that's let's do one, maybe two more levels so that you can see what kinds of things we have to do. So now we have a function f from the reals to the reals and a real number t, and the assumption that t is positive. And here's another assumption that f of x is x squared. We just have the parabola of x squared, but only if x is positive. And I'm trying to prove that f of t is t squared. So we know this hypothesis about f for all x as long as x is positive. How do we prove it for this t, knowing that t is positive? So this is called a specialize tactic. So if you click here for more help, it'll say try specializing hf with x replaced by t. So I'll say specialize hf t. That will say if t is positive, then f of t is t squared. But I know that t is positive. That's the hypothesis t pos. So again, it's specialized. So I want to say specialize hf to t pos. That feeds the positivity of t into hf, and the new hf is f of t is equal to t squared. Any guesses for how to finish it? Give you a chance to type it in the chat. Yep, exactly. Maddie, you're not allowed. Come on. You know this stuff inside out. Of course, yeah. Apply was the thing that lets you solve something. So our goal is that f of t is t squared, and we already know that f of t is t squared. So just exactly stick in f of t is t squared. Okay, let me do one more so that you can. I mean, I don't expect you to remember these words. Hopefully, the words are close enough to English words that that they make some sense. that you can kind of remember them even if you saw them only a few seconds ago. Here's another situation. So I have a function f on the reals. I know that there's some value c where f of c is equal to 2. And I want to prove that there's some value x so that f of x squared is equal to 4. So how do I get from one to the other? I mean, again, in natural language, this is completely obvious. The point is, if I know that such a c exists, I want to choose that c. Give me that c. And so the way you say that, if you click for more help, the way to say that is choose choose the c, and so it's not just c itself, but c together with the hypothesis on c, which we'll call hc, using h. H is this big hypothesis. I want to decompose that big hypothesis into two different things. Now I have the real number c. I have the fact that f of c is equal to 2, and I want to find somehow a real number x so that f of x squared is 4. So which real number should I use? Am I going too fast? Is anyone lost? This is much faster, of course, than yeah, of course. This is much faster than how I would uh, talk about this when teaching. I'm just giving you a flavor of what's going on. So of course I would use c, and now my goal is to show that f of c squared is equal to 4. So I'm going to rewrite hc. It'll find f of c and replace it by 2. So rewrite hc, and now my goal is that 2 squared is 4, and that's just ring operation, ring normal form. We'll finish that goal. Okay. And just I'll show you what the big boss of level 1 looks like. Um, so the big boss at the end of level 1 is put them all together. Put all of these tools together. You have a function on the reals. You know that it takes the value value 3 on some input a, and you know that for all x positive, f of x plus 1 is equal to f of x plus 9. Can you come up with a number b so that for all y positive, f of y plus 1 squared is equal to f of y plus f of b squared, all squared? Okay, I'll let you think about that by yourself. But the thing that I wanted to point out is this is something that I really think is difficult for people the first time they're learning real analysis. They have for alls in goals, they have for alls in hypotheses. Those are different things, but they see for all, and they don't say is something in a goal or is something in a hypothesis. They see existential quantifiers in goals and in hypotheses, and they don't distinguish these things. They don't understand if it's in the goal to show that something exists, you have to give me it. Tell me what it is, what you want to use. So that's this 2 by 2 matrix that I'm describing. Oops, this 2 by 2 matrix. What's if there's an existential quantifier in the goal, you have to give it to me. You have to tell me use 6. If it's in a hypothesis, if I know that some function exists or some number exists, then choose that number. Give me that number. And similarly for all statements for universal quantifiers. Okay, so this really locks in the distinction between this side and this side, the things that we know and the things that we're trying to prove. Any questions on this level before I jump to something more mathematically sophisticated? So this is just how to talk lean. You have to learn a couple of these words, and then you can communicate with it. So far, so good. So the point is we're going to build up step by step every one of these tactics, every one of these theorems, every one of these definitions gets built up, one level at a time, and you can see your progress. I skipped level 4. I didn't solve the big boss. Let me jump to lecture 12. There's some interesting things that started happening here. So what I realized is that there are aspects of teaching real analysis in natural language that hide some things that are mathematically actually kind of interesting. So let me skip this level, but let me go to this. Let me go to this second level. So what do you mean you couldn't? Let's just give that a second or reload. Of course you're going to fail the instant people are looking. How else could this go any other way? Amazing. All right, I'll have to go to the official server. Here's the official server. Let's see if that one works. Okay, let me erase my gameplay in case I already did something, but I'll make it relaxed mode and jump to lecture 12. It's good to have a backup. All right, so I'm going to skip over this level and go to this one. Great. So here's the situation. Here's a very common situation in real analysis. Let me zoom in a little bit. We have some property, some true or false statement, but it's not a general true or false statement. It's a true or false statement about a particular number. The example I gave here is the twin prime conjecture. So is the nth number a twin prime or not? Is 3 a twin prime? Well, 3 is prime and 5 is prime, so yes, 3 is a twin prime, but 4 is not. So it's just a function from the naturals to true or false. And let's read this assumption. It says that for any natural number, no matter what it is, there exists some other little n natural number after capital N so that the properties hold, so that the property P holds. So this is another way of saying the property P holds for infinitely many values. And given that the property P holds for infinitely many values, what we want to do is say, so in the case of twin primes, this is a way of, this hypothesis would say, suppose we know the twin prime conjecture. It's saying, suppose that it's true that for no matter what value n you give me, I should be able to give back to you a larger value of little n for which the property holds. Okay, so this is saying there's infinitely many primes. And then our goal is to show that there exists a subsequence. So a subsequence is just a strictly increasing sequence. There exists some subsequence for which, for all little n, when you take p along that subsequence, you get true values for this proposition. So give me knowing that there are infinitely many terms, give me the subsequence which gives me those infinitely many terms. How do you do it? In natural language, you would just say do it, right? Like you would write something like we know that P of n holds for infinitely many n, so let n sub k be a sequence such that P of n sub k holds for all k. You would just write this. It's just obvious that such a thing exists. But why? What is it? How do I get such a subsequence? So it's really subtle things like this that have never been written down in any textbook that I'm aware of that get brought to the forefront. And I guess this isn't necessarily something that trips students up. They believe the statement. They just say, sure, take that subsequence. But then when you have to construct, the fact that it there exists means you have to use something. This is saying use something. So what are you going to use? What subsequence are you going to use? So here's where it gets really interesting. You get to say things like this. So there's a hint here, and the hint is to write the following. So choose, we're going to remember assume something existed. So the fact that a little n exists, regardless of what capital N you give me, actually means that that's a function. Little n is a function of capital N, and for any value of little n of capital N will be greater than capital N, and P of little n of capital N will always be true. So that's what this choose is going to accomplish. I'm going to copy and paste this choose, and you'll see that what happens to the game board. Let me get rid of the writing here. So this was the original game board, and here's the new game board. The new game board is, I called this function tau because I don't like n to be a function of natural numbers. That just seems weird to me. So I called it tau. Tau is a function from the natural numbers to the natural numbers. Given a natural number capital N, it returns this little n. And the reason that it does that is because what that little n is supposed to do is have two properties, that for any value of capital N, this little n exceeds capital N, and for any value of capital N, this little n at P is true. So we get this hypothesis on tau with a bound and hypothesis on tau with p. And out of these two things, you're supposed to come up with a subsequence. So what's really going on, again, as a picture, what's going on? Where's my little drawing app? Okay. So what's going on if I look at the graph of tau, all I know about tau is that it stays, whatever the value of tau is on the natural numbers, that value stays above the line y equals x. That's what this hypothesis tells me. And yet, what am I supposed to do to get a subsequence of values where of tau, which is monotonic, strictly monotonic? Any guesses? I realize this isn't something probably any of you have thought about before. You've never had to. Well, so here's the idea. Let's start with 0. So if I start with n equals 0, then I get some value of tau, whatever it is. I can't control what it is. All I know about it is that it's strictly positive. So this is tau of 0. Maybe tau of 0 is 37. I need to get a next value I need to get some next value so that the tau of that value is more than 37. Well, 37 is over here. How do I ensure that the next value is more than 37? Iterate. Exactly right. I'm gonna apply tau. Tau of 37 is guaranteed to exceed 37. And remember, 37 was tau of 0. So this is actually tau of 0. And so the way to get a strictly increasing subsequence, because tau itself is not strictly increasing, tau can bounce around all over the place. But the way to get a strictly increasing sequence is to have sigma, which takes the natural number n and maps it to tau to the n of whatever your favorite starting point is, 0. Okay, so that's the sequence that you need to use here. So if I clear the drawings, let me get a little bit more help. Let's define this function. I'm going to define the function that goes from the naturals to the naturals. Where does it send the natural number n? It sends it to tau to the n. And for technical reasons, you actually want one more step. You don't want 0 itself, but you want tau of 0. So it's really iterate it one more time to force it to be strictly increasing on all values. The reason is I know that p of tau of anything holds, but I don't know that p of 0 holds. So I can't start it at 0. I have to start it at tau of 0. And then you can continue I won't finish the proof for you. I just wanted to highlight this little idea of iteration, this orbit, which was always there. This is about mathematics. This isn't even about teaching. It was always there. It just was never brought to the forefront. Let me jump now to one more example before I show you sort of how it's going. So we're up to the real numbers and the construction of the real numbers. And again, when I discuss this, I use the device of a conversation between Simplicio and Socrates, and we talk about how to extend the natural numbers to the integers as equivalence classes of products, pairs of natural numbers, and how to do operations on those, and then we build up to, okay, so they already know about Cauchy sequences, they know about Cauchy sequences of rationals, and so the reason, here's the big reveal, is that the reason that Cauchy sequences of rationals converge to real numbers is that Cauchy sequences of rationals are real numbers. And then, of course, okay, so Simplicio says, no, duh, you telegraphed that from a mile away. And, they have some fun in this discussion. But, so again, so 3 is built from the natural numbers. The natural numbers are just 0 and the successor. So 0 is a natural number, then the successor is 1, the successor of that's 2, the successor of that is 3. Then 3 comma 0 turns into an integer, then 3 over 1 turns into a rational number, and then this infinite sequence, 3 over 1 forever, is what this up arrow casting is doing. Anyway, I'm not going to get into that, but here's the kind of theorem that I think is easier to prove formally than it is to prove in natural language. And this is where I made a little change to make it easier to see, and I would really love for the game server to come back online. but I fear it won't. Okay, so we'll just do it here. So here's the situation. I want to prove the completeness of the real numbers. So is uh, what we know is that we have, let's say we have a sequence of real numbers. And let's say those real numbers form a Cauchy sequence, but actually each real number is itself a Cauchy sequence of rational numbers. And so what we really have is a matrix, is a map from the naturals to the naturals to the rationals. It's a matrix where the first row is a Cauchy sequence converging to x0, and the second row is a Cauchy sequence converging to x1, and so on. And then the x's themselves are Cauchy. So the way to say that is we have this matrix Q from the naturals to the naturals to the rationals. We have the fact that for all n, Qn, which is now a row, is Cauchy. And then we have the fact that the x's are Cauchy, which says for all epsilon exists in n, so that for all m and n after capital N. Now this real of cow thing is the fact that we proved Cauchy sequences converge to real numbers. So if you know that a Cauchy sequence, if you know that a sequence of rational numbers is Cauchy, that gives you a real number. So this is like xm minus xn is less than epsilon. That's exactly what this says is that the x's themselves are Cauchy. Then what we want to prove is that there's a sequence of rational numbers. Somehow out of this matrix of rational values, we're supposed to come up with a sequence of rational numbers, which is themselves Cauchy, so that the sequence of limits of the xn's, this is the xn's, again, this is why I refactor things so that it would look nice, is the real number limit of the y's, and the reason it has a real number limit is because it's Cauchy. So this is like a really, really technical thing that is very easy in natural language to get lost in what's going on. And formally, this is what it looks like. Now, I won't go through the proof. Let's not go through the proof together, but I'll just show you kind of what it looks like under the hood, or what it would look like if the game server was running. So here's what it looks like when I'm working on it. Here's the statement again. So the way that I've set it up, maybe I'll make this just a little bit bigger. Maybe the better way of setting this up is we have this map of the rationals, and we have a sequence of real numbers. We know that every row of these rationals is Cauchy, and we know that the sequence of x's is also Cauchy, which is this vertical thing. And we know that the x's are these real numbers that come out of the fact that the rows are Cauchy sequences. The xn's are the limits of the rows. Then we want to construct a rational sequence that's Cauchy, so that the limit of the x's is the limit of these rational numbers. Okay, let me not go through the proof, but the point is it's something like a diagonalization argument, but the naive diagonal doesn't work. So the Q00, Q11, Q22 diagonal, literal diagonal doesn't work. What you have to say is, at row 1, eventually we're going to be within some small amount value of x0. And in row 2, eventually we're going to be within some amount. But students get really confused because they know that they have to do that given an epsilon. How do you do this for all? I don't have an epsilon. The first thing I have to do is give you the sequence. How do I do that? And the trick is you make row 1 within 1 of x0 by going sufficiently far out. You make row 2 within a half of x1. And you make row 3 within a third of x2. And row 4 within a quarter of x3. And for each one of those, there's a distance you have to go into the row before you can do that. And so all of this, I mean, we took an entire lecture to do it, but it's something that I think is done much, much more easily when you can see it live and you can see the game state changing line by line. I mean, I'll just dump, since I haven't given you enough time to really learn what's going on, I'm just going to dump a few of these lines into here, and we'll see if it's working. Yeah, okay. This needs to be fixed a little bit. But the point is, the way it's set up, you're not going to see what I want you to see there, but maybe you will here. And so here's the trick is that the y is some kind of diagonal argument, but the second index is not just the naive QNN diagonal, it's QN and some value, which this sequence n is like that subsequence that goes far enough out for every row, there's a value that when you go far enough out, you'll be within 1 over n plus 1 of the nth term. All right. That's maybe not something that's so easy to look at, but the point is uh, that's that's real analysis. Real analysis is tricky. So let me pause there if there are any questions about the game. So far, so good. Everything kind of makes sense.
Are you creating all of it from scratch, or I mean, I imagine like definitions and all the tactics are already in place from Lean, right? But like kind of like the structure of like, oh, like you have this lecture, and then like we're going to do these particular problems, like that is you're doing, right?
Yeah, that's all from scratch. And the problem with Lean, and specifically MathLib, the library, is it's way
Mhm.
too powerful. So it doesn't have epsilon delta definition of limits because epsilon delta is too babyish for them. They go straight to filters. They go to the most
Mm.
general thing. And so actually we have to develop everything from scratch so that we don't do it's like if you're teaching Riemann integration, you don't say Riemann integration is a special case of Lebesgue integration. I'm just going to teach you Lebesgue integration. No, you actually have to develop Riemann integration. So I'm actually having to develop all of these things from scratch.
Oh, okay.
But they're very natural. I mean, the code is all public, by the way.
Hmm.
If you click on you can click on the course website, but also here the link from the main website takes you to the code, and then you can see every single level. I mean, everything is completely publicly available. Uh, Let me jump to some level where there might be a definition or something. Um, there's some discussion, and then there's a little theorem, and here's what the hints look like. Here we're proving the Archimedean property that no matter how small epsilon is, there'll be a natural number greater than 1 over epsilon. And why is that true? Yada yada. Um, so everything's kind of open source, and anyone can download this themselves and make their own video game out of it. Um, LLMs, I use LLMs all the time to help with doing things here. But let me jump to what so their homework is to play the game and to write out by hand their solution to the game. And so the question is, does this actually work? What does it look like in practice? So this was our recent midterm. They had not seen the definition of divergence to infinity, although they've seen many definitions very much like it. So what does it mean for a sequence of real numbers to diverge to infinity? It's that no matter how high a bound you set, there's always some value of n, so that if you go farther than n in the sequence, the a of m will exceed that bound. Okay, so that's what it means for a sequence to diverge to infinity. Not just diverge, it's not just the negation of convergence, but it's divergence up higher and higher and higher by going far enough out. Okay, and then they were asked to give a formal proof in Lean, but there's no Lean. This is all on paper, timed in the classroom. And the question is, have they gotten to the point where they can move knight f3, knight f6 in their minds? And I claim that they have, and let me demonstrate that to you. So they have three objects, three sequences, A, B, and C, sequences of real numbers, and a real number L. I assume that A diverges to infinity. I assume that B converges to L, and the student reminded him or herself what that means. That means that for all epsilon positive, there exists an n, so that for all n greater than n greater than capital N, Bn minus L is within epsilon. Okay, so that's what seq lim means. Div to infinity, we just learned that definition, so of course the student reminded themselves what that is. And I assume that the limit is positive, because of course if the limit is 0, then this isn't true. Even if the limit's negative, it's not true as stated. The hypothesis on C is that Cn is An times Bn. So the product, if you take if you take B that converges to a positive limit and A that diverges, then the product also diverges. The goal is to show that it diverges. Okay? And the solution is verbatim the solution that you would get if you would put it into Lean. So first of all, the goal is divergence to infinity, but I want to see what that divergence means. It means that for all m there exists an n, so that for all n greater than n, Cn is at least n. Then the next step, give me that m and give me the assumption that m is positive. That was the intro tactic. Next step, specialize HB. HB says for all epsilon, what epsilon do you want to put in? He wants to put in L over 2, together with a proof that L over 2 is positive, knowing that L is positive, which is a tactic called bound. How about HA? Well, it turns out that you want to say, you want to apply HA not to an arbitrary M, but to 2M over L, where M was the M that came out of the goal. This is the kind of thing that once you say it enough times formally, it becomes easier to say it formally than informally. It's much more awkward to say these things informally. Okay? And then yada yada, the proof continues. There are some inequalities here that are solved by bound, and then it's linear arithmetic on the fact that A times B is at least A times L over 2, because B is at least L over 2. And then A is at least 2M over L. That was the construction, which means that, and this product is of course equal to M. And you combine these things together, you get exactly what the point was. And I asked not just for a formal proof, but also a natural language proof. Does this person understand the natural language of what they've written out? And of course, it's very hard to write a perfectly formal proof if you can't also write a very, very nice natural language proof. And what's the natural language? A sequence diverges to infinity, and B converges to L with L positive, then their product diverges to infinity. Let M and with M positive be given. Then there exists some n2, so that for all n greater than n2, Bn minus L is within L over 2. There's also an n1, so that An is at least 2m over L. It's enough to show that for all n greater than the sum instead of the maximum, because the sum is easier to deal with when you're working formally, the product is at least m. That's the goal. They're very, very careful about what's a goal and what's a hypothesis. They're not mixing this up anymore. It's all been very, very explicitly spelled out for them on the game board, and they can see the game board in their mind, so there's no, they're not making those kinds of errors anymore. So we know that An is at least 2m over L. We know that Bn minus L is at least, at most, L over 2, which means that Bn itself is at least L over 2. And so this product is at least M. So it seems to me the experiment's working. You know, it's certainly not seamless. There are a lot of paper cuts, but overall, I would say the null hypothesis was that this experiment would fail, and I am not able to verify the null hypothesis at this time. So I'll stop there. Thank you.
Let's thank Alex. And before there's any questions as well, yeah, I thought I have some, but yeah, let's see if anyone wants to ask something first. You can unmute yourself or like just type it on the chat.
I should say Maddie is the TA for the course, so she's a huge, huge help, and I wouldn't be able to do anything without her.
And do they bring their on a regular, say, class? Would they bring their computers, or do you just discuss together? How would you?
Not only do they not bring their computers, they're not allowed any technology.
Oh, okay.
So the first thing they do when they walk into class is they take out their phones, they turn them off, and they put them in their backpacks. And they sit with paper and pen, and we just lecture on the, quote unquote blackboard. I always have, where is it? I just start with a blank screen, and we start, computing things, and we talk, and I'll have the game. Maybe I'll have the game here in the background as I jump back and forth uh, between the handwritten stuff and the game. And that's what you see in the lectures as well. I mean, that's what this is all the handwritten stuff that gets recorded. But then the lectures themselves, you can see side by side with the conversation is this. So no, they're sitting at their desks with pen and paper. They take a quiz every single lecture. I audible. I just say, okay, here's a good, do you understand what's going on here? Write down what you think the next line is. So they're constantly testing their own understanding, that kind of thing. They're a shy bunch. Nobody wants to know anything.
So,
Jim?
uh, it's interesting how you teach with no technology. This is a fascinating game situation. In linear algebra, I do the opposite. They have technology, but they have to think in real time.
Uh-huh.
And they use the technology to look things up so I don't have to spend time. And then I write on the board, okay, here's the beginning of a proof. Now look up, don't look down. Who has an idea about what to do next? And if you're stuck, you can look down and then I'll wait. And then a big discussion happens. So
Uh-huh.
it's fascinating the way you do it this way.
Yeah, I've given myself all the technology and taken all of theirs away, and you've done the opposite.
Yeah,
You've
but they
made
have
it a blackboard.
my students have to think in real time.
Yeah.
So this is an interesting teaching approach.
Matt?
Yeah. Have you thought about like, so what I'm thinking right now is this idea of if they were to like go on to a class that uses this proof stuff that isn't lean based, do you
Yeah.
think they can take a natural language statement? So the example you showed was a lean statement that they converted into natural language. They have to go the other way.
So most of the exam was purely natural language.
Oh, okay, okay,
Uh,
okay.
Precisely because I'm teaching them real analysis. I'm not teaching them lean.
Right, yeah.
The lean should be a tool for real analysis, not the other way around.
Okay, okay.
And so most of the exam is natural language, and only some of the components, this would be very painful to do in lean right now.
Yes.
Um, so that's why it's not in lean. It's just, can you do it? And here's the explanation. And yep, you know.
Okay,
But
okay.
the hope is that doing things this way, just the threat of lean hovering over them makes them that much more precise about what they say and
Mhm.
just clarifies what's a hypothesis, what's a goal. This is the thing that I find I always dreaded the other times that I've taught real analysis. Grading these things is so dreadful because they've confused what they're trying to prove with what they already know and vice versa. And it's all over the place. Whereas now we have this very, very clear divide between hypotheses and goals. Goals break down into sub goals. They can, if they have to prove P and Q, they know how to split it into a proof of P and then separately a proof of Q. Um, so all of that is in there and it's handled by the game, and the threat of the game of needing to talk to the game forces their natural language proofs to be clearer. That's my claim, and I can't. Well, my claim is a negation of that, and I can't disprove the negation. That's as strong as I'm willing to place on it right now.
Cool. Sounds good.
Any last
Yes,
other
I do
more
have a
questions?
question.
Hi, Sheila.
Hi. Alex, I noticed you have levels, so you introduce level of understanding for students. In addition to levels and gamification in their learning, do you give them badges or like do you have characters or like what other gamification like components you integrate in the class?
This is the only gamification. I haven't gone as far as badges or any other bells and whistles. They just, they have problem sets. By the way, the problem sets are also now natural language problems. There's a bunch of problems they're supposed to solve in natural language, together with problems that they should solve formally. And the nice thing about the formal problems is they don't need it to be graded. They know if they got the solution or not. Lean will tell them, yes, you've solved this. They're finally at the point where they can prove 0.999 is the same thing as 1. Officially, rigorously. So no, I don't do more gamification than the massive amount of gamification that's already here. Every lecture is a world. Some worlds have big bosses at the end. Um, so here's the big boss here is the proof of Bolzano-Weierstrass. And we're on to series, and soon we'll be on to Riemannian integration and so on.
Thank you. Thank you so much.
Thank you.
And is there like do you know if there are any other courses of structure in a similar way, like where like because you already are writing this for real analysis, right? So I imagine like obviously like something like Euclidean geometry, you can kind of do it at like a la Hilbert, right? Like with all the axioms where like they had to prove like like all these proofs like that they thought like were complete, but they were not really complete until Hilbert like axiomatized. So is there like a similar thing there, like that you have found or you want to do?
So this past summer, oh, I don't have a link to it here. Let's see, how am I going to find it? GitHub. I can't see behind this Zoom stuff. GitHub. Um, I'll just put a link in the chat to something. Oh, come on, I deleted that. Okay, wait, I can get to it from here. Repositories, and is it here? Where is it? Where is the Euclidean? Oh, maybe it's in here. Here we are. Summer geometry course. Here it is. Formal Euclidean geometry. So this was a summer course that I'll put a link in the chat. This is a summer course that I taught to high schoolers. Oh, this is the one with only 4 um, lectures. Where's the version with more? There's another version with more lectures. Let's see. Where are all the repositories? It was Euclidean geometry. Here it is. And where's the what's that called? I guess it's just this website. Okay, so I had a student who was helping convert this website, which is not so nice, into the second one, which is nice, but we only got through
Mhm.
lecture 4. Anyway, so this was a complete discussion of Euclid's Elements Book 1, and how do you fill in the missing axioms, and we go back and forth between Desmos and Lean and try to keep track of everything. So this is for high schoolers for how do you do formal Euclidean geometry.
Mhm.
And it wasn't in the game, but maybe I'm not sure if yeah, maybe it could be made into a game. Part of the interest here was how do you we didn't I didn't just give them the axioms and then we started proving theorems. I said, what should the axioms be? That was kind of the most interesting part of the discussion. Anyway, you can peruse that if you like.
Mhm.
But yes, as far as I can tell, 10 years from now, every single course in the department past 300, because you actually have to prove things. You can't do 151 because you're not proving things. Uh, Past 300, any proof-based course, at least in theory, well, definitely in theory, if not in practice, uh, could be a video game.
Perfect. Maybe if anyone has a last minute question, like just because we're almost like at the end of the time. Oh. Otherwise, let's thank Alex again. I will once we have uploaded the video to YouTube or somewhere else, like I'll share it with everyone the link. But yeah, it was a great talk. So thank you so much for being the first one as to give it as well.
My pleasure. Thank you.